So let us look at this question. So in this question, what we have is we have a particular ride in an amusement park. And in this ride, you have a carriage of total mass 5.0 times 10 to the power of 2. I'm going to work in terms of arbitrary quantities. So I'm going to label this M. And for this carriage, it's going to be pulled up to the top of a hill at point A at a height of 25 meter above the ground. So let me just label HA. The carriage itself is going to be released from rest. So initially, it's going to be at 0 meter per second. And it's going to loop the loop. So it's going to come down and loop. So it's going to move down and loop the loop in a vertical circle as shown. The loop itself, we are told, has a diameter of 14 cm. I'm going to label this as HB. Okay, and throughout the whole process, you can assume that frictional force is going to be negligible. And when not mentioned otherwise, air resistance is also going to be negligible. We always consider ideal case unless the question hints us not to do so. So in the first part of our question, let's go quickly to the first part of question. You're asked to show that the speed of the carriage on reaching point B is 15 meter per second. So how are we supposed to look for the speed of point B? If you look at the question, we are obviously not going to use equations of motion because throughout the whole process, the acceleration on the carriage, because the force acting on it is actually quite complex. There's normal contact force, then there's weight, and there's different angles to consider. The acceleration on the carriage is not going to be constant. So we are definitely not going to look for the speed using the equations of motion that we have learned in kinematics. So how do we find the speed? When all that fails, we'll use conservation of energy. So I'm going to use conservation of energy to show that the speed on reaching point B is 15 meter per second. So I'll do it here. So it is a show question. You'll need to write down very clearly all the concepts that we use. The concept I'm going to use here is conservation of energy, and I'm going to apply conservation of energy between point A and B. All right, so these will be the 2 points where we apply. And since there is no frictional force, there's no air resistance, then there is no external work done by anything. So we will assume, we'll be able to assume that the initial kinetic energy plus the initial potential energy of the system is going to be equals to the final kinetic energy plus the final potential energy of the system. So what forms of potential energy do we have? Gravitational potential energy. And to apply gravitational potential energy, we will require us to set the point where gravitational potential energy is 0. I'm going to measure with respect to the ground. So what we can write now is kinetic energy at A plus the gravitational potential energy at A is going to be the kinetic energy at B plus the gravitational potential energy at B. So what's the kinetic energy at A? It is 0 because it's half mv squared, the initial speed is 0. So this is 0. And then what's the gravitational potential energy? So it is mgha. Kinetic energy at B, this is what we want because what we want to find is the speed at B. So we'll have half m vb squared plus mg hb. With this, you can substitute in your values. You can make vb the subject of the formula. All right, and you should be able to solve for it. M is negligible. Not M is negligible. You can M is common in the equation. Of course, you can cancel that out. So show all your working, show all your substitutions, and you can work this out, and you should be able to find that VB is 14.7 meter per second. Please show all substitution because this is a show question. All right, let's move on. From here, the question wants us to label on the figure below, and it switches from energy to a force approach on the forces acting on the carriage when it is at point B. So let's look at the forces acting on the carriage. So the carriage has mass. Definitely, it will be having a weight. And since this is an exam question, please remember to name and label all your forces. So mg is the weight of the system or weight of the carriage, and then we will also have it is resting on it is actually pushing against a track because it has a velocity here. All right, so I shouldn't do this. I should not label the velocity. Okay, on the diagram itself, it has a velocity, and therefore it will be pushing against the track. So the track itself will also apply N, a normal contact force, onto, N, a normal contact force, onto the body. All right, so please remember to label. All right. Operators of this right must ensure the speed at which the carriage travels at point B is above a certain minimum value. Okay, minimum value for what? Minimum value for it to remain in contact. So determine this minimum speed. So let me quickly explain why a minimum speed is needed. Let us consider the extreme case whereby this carriage reaches 0 meter per second at this particular point in time. Then what is going to happen? If in the case it is 0 meter per second, it will suddenly come to stationary rest, and then it's going to fall off. So what it's going to do is it's going to move up, come to a stop, and because there's no velocity to keep it continue moving, let me remove this track. Yes, mg, it has no velocity to keep it moving. The next moment in time is going to drop down. So it's definitely not safe for this to happen. This is not what we want. What happens if it has a speed, but the speed is not high enough? So if it is not high enough, it still has a little speed, but it has both mg acting on it. The next moment in time, the speed is in this direction and it has an acceleration downwards. It's like projectile motion. If your projectile motion is not such that the curvature can match the curvature of the track, it is also going to lose contact and going to go down in this direction. And this is also not what we want. So the speed must be sufficiently large such that it has, when it has a speed here and it has the gravitational force acting on it, the parabolic motion curvature in the initial part will match that of the track, and then it will be just in contact. Okay, so at this point in time, n is equals to 0. What happens if the speed is larger than this particular speed where n is equals just in contact when it is just at the top? Then what it will have is, if the track was not there, it will subscribe a parabolic path that is going to be bigger, okay, in radius than that of the track. All right, so the curvature, the radius of curvature is going to be bigger. But because the speed is very, very high and the track presence is down there, so the next moment in time or during this moment in time, the track will also exert a force acting on it, and you will have both the normal contact force and mg to force the carriage back in the circular motion. So what we have is that in reality, if there's a normal contact force, N plus mg is going to provide for the centripetal acceleration to keep the carriage in circular motion around the track, and that is equals to MAC. So the minimum speed required is when you just have enough velocity together with the acceleration, which is your weight, to match the curvature of the track, and at that point n is equals to 0. So this is why we have this answer for part 3, where you want to find the minimum speed such that the carriage travels at point B. That happens when the weight itself just provides for the centripetal force required. For the circular motion. And your normal contact force is equals to 0. And when that happens, you will have mg equals to m v mean squared over r, and then this will cancel and you can work out what the v mean is, and v mean is square root gr. Substitute in and you should be able to get 8.3 meter per second. So this is the answer for part 3. Alright, next part of the motion, we're going to now move the carriage, and it's subsequently going to mount a low hill in this part of radius 15 meter. Determine if the carriage will remain in contact with the ground. So again, the keyword is about contact. So what are we looking at? So if you are looking at the object at C and you are trying to analyze this circular motion, all right, then what we will have is to determine whether it is in contact. Then we are looking at what is the value of n. If n is equals to 0, it is just in contact. If it is traveling too fast, then what will happen is that when you try to put in and solve for the n, you will find that n will end up to be a negative value. So what it means that it has already lost contact way before that. So this is what we are going to use. We are going to see whether we are going to get n equals to 0 or in fact n less than 0. So to do that, of course, it's a forced approach to doing question. The next thing we need to do is draw a free body diagram for this particular carriage at point C. I'm going to move down and draw the free body diagram and solve it separately here instead. So this is part 4. I'm going to just transfer here. So this is point C, and then what we have is we have the carriage down here. We're going to assume at this point in time there is going to be a normal contact force. So there's going to be an mg. The center of the circular motion is somewhere below, and we know that the radius of the circular motion, according to the question, is 15 meters. If it stays in contact, there will be a normal contact force, but overall, if it's going to be in circular motion, the centripetal acceleration should point towards the center of the circle. So with this, we can now apply Newton's second law. So we're going to say that by Newton's second law, mg minus n is going to provide for the centripetal acceleration. Okay, so mg minus n, we are working with speeds here, so I'm going to use the form of mv squared over r for the centripetal force. Alright, so from here, we are interested in n, so I'm going to make n the subject of the formula. So if I make n the subject of the formula, I will have n equals to mg, bring it over the other side, and then I will have mg minus mv squared over r. Alright, so what we need to do is we will need, okay, the velocity at point B, according to the question, if you read carefully, the speed does not exceed 10 meter per second. So we're going to use that as the limit. So we'll put that in, and you will be able to get m. Let's take out m. We'll have 5.0 times 10 to the power of 2. G is 9.81 minus 10 squared. The radius of the curvature is 15. And that works out to be 1,600 Newton. So this value is not equals to 0, and in fact it is bigger than 0. It tells you therefore it's going to stay contact. N is positive. Therefore it means that carriage will stay in contact. Done.